Hello everyone. In this video we will be learning analytical technique, and the technique that we learned today is the mass spectrometry. We use this for multiple reasons, and I will discuss that in detail as we move forward. But before we get into any detail, here are some examples. We have atomic absorption spectrometry, infrared mass spectrometer, nuclear magnetic NMR spectrum. That NMR spectrum could be for hydrogen, carbon, or nitrogen. So these are all analytical techniques. Before we get into the mass spectrometer, let's talk about the hydrogen deficiency index, how to calculate IHD, the index of hydrogen deficiency. You will be given a formula, and from that formula you need to calculate what is how many hydrogens it is short of. So it is pretty simple process. There is not much rocket science in this. We have learned organic chemistry, and it has a lot to do with organic chemistry. So for any organic chemistry, if it is a saturated compound, we know that a saturated hydrocarbon, the formula for that hydrocarbon should be CnH2n plus 2. So CnH2n plus 2. That is the number of carbon atoms for any n number of hydrogen atoms. So if I have Ca4, that means your hydrogen will be 4 multiplied by 2 plus 2. So you should have 10 hydrogen atoms for 4 carbon atoms. Now if the molecular formula that you are given has any less hydrogen atoms than 10, that means it is deficient of hydrogen. That's all it is. So if any of the bonds are replaced, how does it get deficient? If a single bond is replaced by double or triple bond, of course it will have the deficiency of hydrogen atoms. By determining the IHD, which is the index of hydrogen deficiency, we can tell what is from the molecular formula if there are multiple bonds, or if there are rings. It's an aromatic compound. The IHD is a number of hydrogen molecules it would take to make the structure saturated. So basically the concept is based off of that I want to have 1, 2, 3, 4 hydrogen atoms, 4 carbon atoms. And for 4 carbon atoms to have a saturated structure, it needs to have 1, 2, 3, 4, 5, 6, 7, 8, 9, and 10 hydrogen atoms. So any less than that, for example, I have 8. Okay, if I have 8 hydrogen atoms, that means I'm short of 2 hydrogen atoms. That means there is a double bond somewhere in the compound. If I have 6 hydrogen atoms, there could be a triple bond somewhere in the compound. So basically that IHD is calculating if I have a double bond or a triple bond in the compound based on the number of hydrogen atoms I'm short of. So there are a couple steps that you can take to calculate how many hydrogens it is short of. And by the way, when we calculate the hydrogen number, we are calculating it for a molecule, H2, no, not for the hydrogen atom. So to calculate the IHD, here are a few steps. The first step is calculating the maximum number of hydrogen atoms for a molecule. So first of all, I need to find out that based on N, how many hydrogens I should have. Once I know that I should have, for example, in this situation, I should have 10, and suppose that I had C4H8. So my second step will be that from the maximum number of hydrogen atoms calculated in step 1, deduct the number of hydrogen atoms that are in the formula. So maximum is 10 that I'm expecting, and I actually have 8, so I deduct it, I have 2. Now once I calculate this 2, I will divide it by 2 because I am calculating for a molecule. Okay, I'm calculating the deficiency for a molecule. So 2 divided by 2, the IHD will be 1. If the IHD is 1, that means there is a double bond. If 1 IHD, that means it's a double bond between any 2 carbon atoms. If the 2 IHD is 2, that means I have a triple bond. If IHD is 3, that means it's an aromatic ring. That means you have a, some kind of a cyclic compounds or benzene ring or something like that. But there are some other things that we have to see. What if it is not a pure hydrocarbon? What if it is, it has other elements in it? So if you have any halogen atoms, then as you subtract the 2, you subtract that number of halogen atoms as well. So count halogen atoms as hydrogen atoms because they also make only one bond with carbon. If there are oxygens, then we do not care for the oxygen. Oxygen has no impact on the IHD. For every one nitrogen atom, you will be adding one number to the hydrogen deficiency. So let's apply these rules in this example. I have C3H6. So for C3H6, based on CnH2n plus 2, C3, I should have 2 times 3 plus 2. So C3 should have 8 hydrogen atoms. So maximum number of hydrogen atoms is 8. I have 6. So when I subtract, I get 2. I always divide by 2, so the hydrogen IHD is 1. This is for a plain hydrocarbon. What if I have a compound that has nitrogen and halogens in it? Again, I calculate the maximum number of hydrogen atoms, subtract the number of hydrogen atoms that I have, so 14 minus 12 will be 2. Now as you see, I have 2 nitrogen atoms. So for 2 nitrogen atoms, I will add 2 because for each nitrogen atom, I add 1. Okay, I add 1 for each nitrogen atom. I have 2 nitrogen atoms. So to this 2, okay, I will add 2 for nitrogen. That makes it 4. Now for each halogen, I subtract 1. I have 2 halogens. So 4 minus 2 will be 2. And then always divide by 2. So it is IHD is 1. So as I told you, if IHD is 1, it's a double bond. If IHD is 2, it is a triple bond. If IHD is 3, it is an aromatic ring. All right, so if we understand what we were talking about, I want you to go ahead and practice the following compounds and calculate the IHD, the index of hydrogen deficiency for these compounds. Going forward, we will be talking about mass spectrometer, mass spectroscopy. Mass spectroscopy we learned in atomic structure unit. We learned that we calculate the mass to charge ratio using this process, and it's fingerprinting. We can tell exactly what the molecule is like, how it's fragmented. I will explain that in a second. But just to go back, it has 5 steps. These steps used to be part of the IB syllabus, but not anymore. But there is a possibility they just ask you write the steps in a proper order. So the first one is vaporization, that we take a molecule and we knock off an electron. First of all, we convert it into a gaseous state, vaporization. Then knock off the electron to convert it into an ion. So M plus ion, that means molecule ion. So this M plus ion is the whole molecule. We are not losing anything, but only an electron. So it ionizes. So the sample is bombarded with a stream of high energy electrons to ionize it. Then we accelerate it. So it's vaporized, it's ionized, and it's accelerated. Okay, so we had a pause here. I hope I can catch up where I left. I was talking about the process of ionization and detection. So as I said, it gets vaporized, then we ionize it here. That means you take the electron out of it, so it becomes a positive ion. And then from there, it is accelerated. And after the acceleration, it's detected. So once you detect it, this is what you get. And this is what we are supposed to read and find out what the formula is, or how the structure is. So this is the whole process of mass spectroscopy. But let's go back. That what do we use it for? So the mass spectroscopy, we use it to determine the molecular mass and the molecular formula of an unknown organic compound. The structure of the molecule is determined by breaking the molecule into ionized fragments. So let's say you have C2H6. Once we ionize it, or let's say you have chlorine on it. So let's make it a ethane. So once, as I said, it's vaporized. After vaporization, a beam of positively charged particles come in, and it can take off the electron. Once the electron is gone, it becomes a positively charged molecule. So you have chlorine here, and chlorine does not have the complete electron, so chlorine becomes positive. Now, since chlorine is, so this thing whole here, the whole molecule as is will be M positive, a molecule with a positive ion. So this M positive will give us the basic peak on the spectrum. Basic peak on the spectrum. So keep it in mind. This was our original molecule. We ionized it by taking one electron off. It has a positive charge. So this is M positive. Now what happens, since it is electronegative, electrons are more on this side. Some compounds are so fragile that even one beam can break it into pieces. But usually what happens is that once it becomes a positively charged ion, it can break it off right here, and that's what we call fragmentation. So it breaks into fragments. So one fragment can go out as this, Cl neutral or Cl negative. It will take the electron away from it, and this becomes positive. The leftover part becomes positive. Another thing is that when it is detected, only ions are detected. Anything that breaks off as neutral does not get detected. So positive ions get detected, the neutral piece does not get detected. So if it has a positive charge, you will realize it. If it doesn't have a positive charge, we will not feel it. But anyway, this is what the fragmentation is about. So once those fragments are broken out, they go through those pieces. We will piece those fragments together to calculate the molecular formula. The identity of the ionized fragments can be determined from their masses. Okay, so each peak is going to be different based on which fragment is broken. Each ionic fragment shows as a peak in the mass spectrum, and the intensity of the peak indicates how many of those fragments are there. So that means that each peak is telling you which fragment is broken, and the intensity, how long the peak is. The intensity of the peak is going to tell you how many of those fragments are there. The most intense peak in the mass spectrum is called the base peak. So this is the base peak. This is where the base peak comes from. And it is assigned 100% intensity or relative abundance. So the peak with the highest mass to charge ratio is formed by the loss of one electron from the molecule, and it's called molecular ion, again, or the parent ion. Once again, this is the one that I'm talking about. The molecular mass, and this gives you the molecular mass, and then we will compare the rest of the peaks with this molecular mass. So when those fragments are broken, they can be broken into different pieces. This information can be found in your data booklet, but you should know, like you're expected to know a little bit of it anyway, that if a methyl group is broken, so carbon is 12, and then with 3 hydrogens it will be 15. The mass of the carbon is 12. So we also, another assumption is, we believe that when we get that spectrums, the peak that we are getting is representing the most abundant isotope. So carbon has 3 isotopes: carbon 12, carbon 13, and carbon 14. Since the molecular mass of the carbon is 12, that means this is the most abundant isotope. So when carbon is coming on this mass spectroscopy, we believe that it is carbon 12 isotope that is being used there. But anyway, if this piece is broken or fragmented, the mass will be lost by 15. If we have the water broken, then the mass will be lost by 18 out of the base mass. Okay, we are doing the math of the base mass. If we have the CH3O, so basically you're adding the molar masses together. So this is how we are going to read this mass spectrum. But let's go ahead and do some practice on this to see how can we read this, because you will be given a chart to read it. So uh, there are two ways to do the mass spectrum. One is, as you see here, that the question may ask you to calculate the average atomic mass of the compound, and you are given the mass spectroscopy. You're given this data. So as you see that lead has the mass of 208, it is mass to charge ratio here, and the relative abundance is on the y-axis. So the mass is 208 and you have 5.2% of it. So 208, 5.2%, that is the relative abundance. Mass is 207, the abundance is 2.2. So we multiply, the average atomic mass of isotopes when we calculate it. So 0.2 multiplied by this, 2.4 multiplied by this, you're taking the percentage of this. So it's 52%, 22%, 24%. So these questions are quite common for your, you did it in honors chemistry class, and then we did it in atomic structure unit. We are usually given the 2%, 24%, 22%, and 52% mass spectra, the percentage abundance. But you must understand now that where those numbers are coming from. They're coming from the mass spectroscopy, and it is basically 2.2. You get 2.2 of those or 5.2 of those, and that's where these numbers are coming from. The rest of the formula is the same. It is calculating average relative atomic mass of the isotopes. So this is one way to use the mass spectroscopy. The second is that we can also use to determine the relative molecular mass. So we will be given an empirical formula, and we will use the empirical formula to calculate the molecular formula. So again, understand the process. We have a compound, and the electron is going to be lost. Once electron is lost, we have a gaseous compound ion, and we will then, this ion will be broken up into fragments. So the largest mass peak corresponds to the parent ion. So the biggest peak is going to be the parent ion passing through the instrument. This is before the breakup happens. The fragmentation pattern can provide useful evidence from the structure of the compound. It depends, how it is being broken. So we will put those, as a chemist, we will put those fragments or these broken pieces together to put together the whole molecule and figure out what the molecular formula is. So let's say here it is. We have ethanol, we have CH3, CH2OH, and this is the mass spectrum of this ethanol. So since we cannot see here very much, I'm going to write it. So I have CH3, CH2OH. Okay, if I calculate the molar mass of it, I have 2 carbon atoms. So 2 carbon atoms will be like 24. Then I have 1, 2, 3, 4, 5, 6 hydrogen atoms, which is like 6. Each hydrogen atom, the mass is 1. I have 1 oxygen atom, so the molar mass of oxygen is 16. If I add them all together, it is 46. Okay, so the molar mass of this whole thing is 46. Okay, I have 2 lone pairs right here on the oxygen. So what happens is that after we vaporize it, we will knock off one of the electron to ionize it. So then this becomes positive. So let's do this. So this becomes positive. So I have one electron still here, and one becomes positive. The rest of the molecule will still be the same. So this is called your ionized molecule, I'm sorry. So ionized compound or ionized molecule. So once it hits the detection board, I detect it right here at 46. So the formula is telling me the mass is 46. That means this peak is coming from the parent molecule. So parent molecule, or M plus. Okay. Sometimes this is the largest peak on the spectroscopy, but not necessarily. As you see here, it is pretty small peak, or maybe the smallest one. But since it is giving you the whole molecular mass, that means this is the parent molecule before it is fragmented, before it is broken.
No, if this is 46 and this is 45, what do you expect here? I mean, common sense, I think, it tells you that it lost one hydrogen ion. So one of the hydrogen ion is fragmented. So what went out? The mass one AMU went out. Okay, that means what is left is 45. So what is left is this. So this is being shown right here. Then this is at 31. So 46 minus 31 is what? 15. So who has the mass 15 here? That if I take just this part here, so 12 for carbon and 3 for hydrogens, that is mass 15. That means this peak is represented by this part, okay? And the fragment that went out is CH3. So the fragment that went out is 15 and what is left is 31. Okay, so this is showing right here. And so same thing, if 15 is left, that means this thing went out and what is the peak is shown by CH3. So this is all this fragmentation is showing that this molecule will be broken down into small pieces. So again, this is right here, the molar mass is 46, the very first peak. Loss of one hydrogen will give you this, that is the 45, the peak at 45. Loss of, so it's right here. Maybe I can manage both right here. So this is 46. This is the parent molecule, the M plus. Then loss of one hydrogen. Loss of one hydrogen is left with this. You know that hydrogen, this hydrogen is lost. This one. So the whatever the molecule left is giving you this peak, 45. Okay. The loss of methyl, which is this part right here. So what is left is this. Okay. Which is giving you a peak of 31. And the loss of OH, which is 16 plus 1, 17. So 45 minus 17 will be 29. Okay, so that is the mass of this is the peak of this thing. So this is how it is divided. Loss of CH3 will give you a peak of 31. So this fragmentation will yield either by you either lose this. There are two fragments. You either lose this or you lose this. Okay, so either you will get the peak at 31 15 or you will get the peak at 31 and the parent peak is 46. All right, so ethanol again, here it is telling you exactly this is the whole parent molecule, you know, only electron was lost, then one of the hydrogen is lost. So this is where the peak is coming from. This is if the CH3 is lost, you know, this is if the whole CH3 is lost, and then what you have here is CH2 and OH. So this is coming from CH2 and OH. That means this part is lost. The fragment that went out is CH3. So 15 is what went out and 31 is left. And here you have C2H5. So the whole thing C2H5, and you know you have the hydrogen is lost. And here it is C2OH. So CH3 is lost. Um, The highest, the highest mass fragment represents the molecular mass of the compound. Fragments provides clue about the structure because certain compounds give you certain groups, certain peaks. Fragments you expect to recognize, as I said earlier, you know, the common molecular mass that you can get from the periodic table. That 15 is for methyl group, 17 is for hydroxyl group. You must understand it has a positive charge. If something is neutral, your detector will not detect it. So you will not realize, you will not get a peak. The peak only comes in if you have a positive charge. But so there is nothing, no explanation here. It is just the molar mass that you're adding. So you can figure out that which peak is getting at what, with which fragment. So that's all about mass spectroscopy and IHD. So in this video we learn about the index of hydrogen deficiency and we learn about mass spectroscopy. So that's about it. I will have a couple more videos for the other two spectrums. Thank you, everybody.